Welcome to the next session where we will be starting, the whole session is called Embedded System Architecture. Before we get into the Embedded System Architecture, we will be looking at some basics of, computing. This is more like, you can say some of you might have studied this in various courses in your college, or you may already have a feel of it. But from my experience, what I feel is understanding this in a little more detail, or at least refreshing these concepts, will kind of help you to understand an embedded system better, what really happens in a computer system. So this is quite basic stuff. Some of you might be very familiar, so please bear with me if it is all very repetitive. But what I have seen is, sometimes these concepts are not completely clear, and I think that leads to some confusion when they try to design things and so on. So this is just to clarify how a typical computer system operates. We'll just start with the fundamentals there, and then we will look at a typical processor architecture. Okay, so that's going to be the objective for this session. We'll look at a computing system introduction. We'll look at how data is typically stored, how instructions flow, typical instruction flow in a microprocessor, a microcontroller. Then you will look at two ARM and RISC architectures in detail. There'll be good sessions on that, where we'll go to a little more detail of both those architectures. These are the two popular architectures in the embedded world. ARM is well established, RISC-V is something which is coming up. Then we'll take an example of one particular microcontroller architecture just to show you pictures or design, software design, different peripherals. We'll look at each one of them and what they do. And then we'll look at the different types of software architectures or design, software design, typical software design for embedded systems. Okay, that's going to be the flow. Okay, let's look at a typical modern digital computer, right? So a typical modern computer today, we can say they follow what is called as a stored program architecture. So what do you mean by stored program architecture? Which means, the instructions for a computer are stored in memory, and the CPU takes that and executes it. And typically the data, everything is stored in memory. So this is typically called the stored program architecture. The name is a very old name, which came, from the starting days of computing, because prior to that, the designs were different. The program could not be stored. They'll have to control things with some switches and all that. So when the first type of memory devices came, and where they decided that they could be encoding and storing the programs into the memory itself, this particular architecture was called the stored program architecture. And typically, there is a unit which is called, the CPU or the ALU, the core of the CPU, the central processing unit. The core is called the ALU, where all the arithmetic and logical operations are functioned. And then you have a read-write memory, where the program and data, everything is stored. Depending on the system, you may also have a fixed memory, which is like a non-volatile, which is called the ROM memory or a flash memory, which is typically used to boot the system. We'll look at some of those examples as we go along. And typically the CPU does only one thing, it continuously keeps executing instructions. The moment the power is turned on, the CPU starts executing. Each processor may start executing at a particular address. They keep executing instructions. Typically it's in sequence, unless there are some special instructions which ask the CPU to go to a particular different location and do it. We'll look at some of those examples as we go along. And most modern computers will have some input and output units. Input units typically like a keyboard or a touch pad or something like that, and output devices which is like a screen or a printer or any other output devices that may be required. So this is a typical architecture which is common. You can look at any modern computer and it will fit into this kind of overall architecture. And there are two broad types. One is called the Harvard architecture, another is called the von Neumann architecture. You can see those diagrams here. So the first one, which is called the Harvard architecture, the difference here is it has you can see here there is a memory called the data memory and another memory called the instruction memory, and you can see two independent buses here. You can see there is one bus connecting to the data memory, another bus connecting to the instruction memory. A bus is nothing but, you can say, a set of lines through which signals travel. That's what a bus means. And in the Harvard architecture, they found advantages to keep the data and instruction memory separately with two independent buses. The reason is, if you think about any instruction, right? You first have to read the instructions, then you'll do what is called as the decoding of the instruction and fetch data. We'll see that in a short while. So it is useful to be able to fetch data and instructions in parallel. That gives you some advantage in terms of throughput and so on. And so that kind of an architecture is called the Harvard architecture. The classical von Neumann architecture, which is here, where it's a single bus and the memory is a common single bus to the memory, where both data and instructions are stored in different parts of the memory. A memory has a range, right? Maybe 2 GB or 4 GB or whatever. Data is probably in one region of the memory. Instructions are in another region of the memory. And typically, when you have such an architecture where there's a common bus which connects to that common memory where both data and instructions stored. That's called the classical von Neumann. Harvard architecture is a little modification of that, where you had two different memory units here, which is like the data memory and the instruction memory here actually. So just to give you a different perspective, that is the two types of architecture that you have. Now we'll move on and see a little bit more about how a typical thing operates and why we are using digital computers. Actually, in the olden days, when computing started, right, the original designs, which people came up with were actually analog in nature. So they started out with doing some analog computation. Actually, interestingly, if you read the modern trends, people are actually trying to see whether going analog for certain applications is actually advantageous in some way. The very latest research for AI and some of those applications, people are looking at analog computing. But the olden days analog computers, the challenge also in terms of the accuracy, right? Analog computers will use voltages or something to do computation. They're used to have something like an op-amp. You can give multiple inputs. The output will be like a sum of two inputs and so on. But the challenge was the precision and accuracy. And analog design, the amount of control you need to have, the precision which you have to design that analog circuitry, it was not easy, right? To get the precision needed, it was becoming expensive. So people slowly came up with the idea of doing digital computation. So a digital computer uses only two levels, 0 and 1, right? The hardware construction is also easier. The hardware is only detecting only two levels, which is like a presence of a voltage or an absence of a voltage, typically maybe 0 or 5 volts in TTL logic. So that's really the two levels which are processed in a digital computer. And the digital computer was, it was easy to build hardware in that fashion because it was very resilient to noise and things like that, because there's a good separation, right? 0 volts or 3.3 volts or 5 volts, there's a lot of difference between the two voltage levels. So it was easy to build hardware circuitry which can sense two levels very reliably and accurately. Then the problem was, okay, I can build hardware like that, but can I do all processing using just those two levels, right? I mean, hardware, just because hardware is easy to build for a binary or a two-state logic, can I do all computation? That's where all the other research and other things, developments happen. So people figured out it is easy to represent information in digital or in binary form, right? In terms of zeros and ones, right? First thing is to understand, how you store it, right? They figured out ways to store numbers, text, everything as zeros and ones. And once that is done, because normally what does a computer do? It processes some information, right? You do some calculations, you add numbers, or you want to, type out some text information. So typically, as long as you're able to represent numbers, text in binary form, then you can do all computation and manipulation on that binary form and get the results that you want. So the developments happen in parallel. So people came up with representing numbers in binary form. That's by using what is called as a binary number system. We'll see that shortly what it is. And the moment you could do that, you could build very reliable hardware to do computing in a very robust manner. Reliability was very important, repeatability, reliability, and you could build digital systems which are very, very fault tolerant and reliable. So that was the advantage. And then, more development happened. You could do things, error correcting codes and all that, right? So even if there are errors, bit errors, they could design codes to correct those errors, and all those development kept happening. But fundamentally, the early shift from analog to digital gave a good boost to the entire development. And they figured out ways to represent information in binary form. Binary is nothing but two state, and digital computers just operate on two states, zeros and one, presence of a voltage or absence of a voltage, right? So that's the first thing to understand why digital. And you can see, this zeros and ones became, the cornerstone of the entire, this is the crucial thing. People figured out how to deal with all kinds of information with zeros and ones. We'll see how it is done. Once that realization came, the hardware development proceeded completely on digital form. Then we had all the LSI, VLSI. They could make the transistors represent, you could build circuits like, from the simple, a transistor, they build flip-flops and registers. Then, you could build all the digital logic, right? Sequential logic, combinatorial logic. You could build complex circuitry. And when the transistors started getting miniaturized, you could do LSI, VLSI. And that is where now you're able to put billions of transistors on a small, piece of silicon, right? So you're able to get extreme, lot of logic implemented at a very, very small transistor, like 3 nanometer or whatever is the current technology people are talking about. And that entire acceleration was due to the shift, early shift from analog to digital. And people figured out ways to deal with information completely in digital form, in binary form. And that's why all the development happened actually, right? Now we look at how do you represent information in a digital form, right? So that's the key to understanding how everything is getting processed. The first thing is, people came up with what is called as a binary number system. What is a binary number system? So binary number system, this is what we're talking about. Binary number system. All of us are familiar with what we commonly use, right? We count from 1 to 10 and so on. We use what is called as a decimal number system, right? In decimal number system, for example, we write, say this number like 125, whatever, right? Sorry. We write, say, number 120. Oops, sorry. Right? When you see 125, all of us are able to relate to that quantity, right? What is 125? It's ultimately a count of something, right? If you look at numbers, you can say it counts things, right? I have pebbles, I count them 1, 2, 3. It's a measure. A number is nothing but a measure of something. It's a count of something. When I write 125, we don't even think what it is, right? We intuitively, if I say 4, you imagine, okay, there are 4 things, right? Count 1, 2, 3, 4. But we don't realize that this 125 is nothing but some kind of symbols again, right? And how do you get that quantity 125 from this 125? We take this 1. You can see this representation right given, right? If suppose say we have 124, how do you get that quantity 124? It is nothing but we take this last digit here, which is 4, right? We take this 4 and we start with 4 into 10 power 0. Then the next position is 10 power 1 and the next position is 10 power 2. So basically this decimal system is called base 10 system. So we get this quantity 124 by taking 4 into 10 power 0 is 10 power 0 is 1. So 4 into 1 is 4 plus 2 into 10 power 1 is 10. 2 into 10 is 20. So 4 plus 20 is 24. Then the next position is called 1. So 1 into 10 power 2, 100. 100 plus 20 plus 4 gives us 124, right? This we have studied early on, like the units place, tens place, hundreds place. But after that, we don't even think about it, right? So all you have to understand is this 124 is what you write 124 is just a representation in the decimal system of the quantity 120. The quantity is important. All of us must have familiar with this Roman numbering system. So we have this Roman numbers here, right? So when you see V, it's a Roman number which represents the quantity 5. So that's again just a representation. So similarly, you can represent numbers using the binary number system, which is called base 2 number system, right? Decimal system is base 10, binary system is base 2. So if I say, and binary system uses only 2 symbols, decimal system uses 10 symbols. What are the symbols in decimal system? Decimal system, the symbols are from 0, 1, 2, and so on till 9, right? 0 to 9, you have 10 symbols, right? That is why it's called a decimal number system. Whereas in binary number system, we have only 2 symbols, 0 and 1. Just 2 symbols in the binary number system. So we have to represent all the quantities using that. The logic is very similar, just like we did this 10 power 0, 10 power 1 for every position in the decimal number system. In a binary number system, we do 2 power. So it's called power of 2, right? So you take, let us take this example, 1011. So this is a number or a quantity which is represented in the binary number system. Like what does it represent? If I had to convert, because for us we understand decimal easily, let's try to convert it into decimal. We can convert it into decimal by just doing this, right? We take from the rightmost side, right? We always start from the first position here, 1. So we take 1 into 2 power 0. Then the next position is another 1. So 1 into 2 power 1. Then the next position is 0. 0 into 2 power 2. And then finally, we have 1 into 2 power 3. So you can see powers of 2, 0, 1, 2, and 3. And what you get, 2 power 0 is 1. So you get a 1 here. Then you get 1 into 2 power 1, you get a 2. Then 0 multiplied by anything is a 0. So it's a 0. Then 1 into 2 power 3 is 8. So it is 8. So if you add all this, you get the value 11. So 1011 in binary is nothing but the quantity 11, which we are represented in the binary number system, right? So likewise, you can actually keep representing multiple numbers. So let's take, maybe let's do some, let me get a blank screen and let's do some simple examples, right? Okay. Let's take, for example, value 0, 0, 0, okay? So what is 0, 0, 0? Obviously, everything. Okay, I think I should. Oh, that is okay. Thanks, actually. So sorry, guys. I think I'm just getting used to this pen here. Once again. So let's take 0. That's it. I think I'll probably sit here. Let's take 0, 0, 0. Okay. So it is obviously all are zeros. You get a 0 here, right? Let's take 0, 0, 1. So what is the value? You can take 1 into 2 power 0 plus all 0, so you can ignore that. So you're going to get a value is 1. Okay. Now if you take 0, 1, 0, this is the next one. Okay. So basically you will see, you'll keep changing this. There are only 2 positions possible. Then you go to the next position. Okay. So you will get 0 into 2 power 0 plus 1 into 2 power 1 plus again 0 into 2 power 2. So you will get the value 1 into 2 is 2. So you will get 2 here. Okay. Then the next higher number in binary number system will be 0, 1, because with the 1 here, again there are 2 possibilities here, right? So we got 0, 1, 0, the next possibility is 0, 1, 1. Okay, so that is, if you check that, it will be 1 into 2 power 0 plus 1 into 2 power 1 plus 0 into 2 power 2. So you will get the value 1 plus 2, this is 3. Okay, now you have exhausted all the combinations of these lower 2 bit positions. So what you will do is now you will make this as 1 and we'll start with 0, 0 here. Then this will become 1, 0, 1. This will become 1, 1, 0. This will become 1, 1, 1. Okay, and if you calculate like this, you will see this is 4. This is 5, this is 6, and this is 7. Okay. Now, I would like to just illustrate some relationships between the number of bits here and the values you can represent. For a moment, let's assume we are only talking about positive numbers here. Okay. Now, you are able to represent what are the values from 0 till 7, right? We had how many? Each binary digit, 0 or 1 is called a bit. Okay. What is a bit? Bit is nothing but a binary digit. Okay. It's a binary digit. So we had 3 bits here. Okay. And what is the values we are able to represent from 0 till 7? If you see the relationship, you will see 7 is nothing but 2 power 3 minus 1. Can you see the relationship? So basically 7 is nothing but 2 power 3 minus 1. So what the relationship we can say, if you have n bits, you can represent positive numbers from 0 till 2 power n minus 1. Okay, is that clear? So basically what it also means is in binary number system, or it's true for any number system, in binary numbers, the number of bits, the quantity that you can represent, you can easily show by this relationship. So if you have, typically why I'm explaining this is, you hear about 8-bit computers, 32-bit computers, 64-bit computers and all that, right? Typically that tells the when I talk about a 32-bit processor or a 64-bit processor, it talks about the typical register sizes inside the processor. If I talk about a 32-bit processor, most of the registers inside the processor will be 32 bits. It can typically add two 32-bit numbers at the same time, right? So which means I can easily add in the processor numbers like 2 power 32 minus 1 positive numbers. That bigger number I can easily add because it's all done in hardware, right? You want to be able to add it in hardware using the ALU. The ALU can add two 32-bit numbers at the same time. Whereas if we talk about a 64-bit processor, the registers are typically 64-bit, which means it can add much bigger numbers. You can see the relationship, right? As the number of bits goes up, the size of the quantities that you can deal with becomes bigger. So important thing in a computer, when you talk about, people may talk about say 16-bit microcontroller, 8-bit microcontroller. I mean, if you look at 20 years back, most computers were 30 years back, right? I mean, 8085 was an 8-bit processor. So all the registers are only 8 bits. So 8 bits is actually very small. You can add the numbers that you can represent in 8 bits was only from 0 to 255. 2 power 8 minus 255. So you could add only really small numbers. If you want to do even decent computation, you had to write a lot of software to pack the things and split it into multiple bytes and so on and so forth, right? So, but that's where the computing started. But today, all the modern desktop processors that you have are all 64-bit processors, okay? But it's good to understand the relationship between the number of bits that you have and the size of numbers that you can represent. So when you talk about, if you want to represent negative numbers also, what happens is you typically reserve 1 bit to represent the sign, and you use what is called as the 2's complement notation. I'm not going into the details here, but you could probably refer to some articles or good pages and understand how a negative number is represented. You can represent negative numbers by using 1 bit to represent the sign, and encoding information is what is called as 2's complement, which is the most common thing. So if I talk about 3 bits, I can represent values from -4. I can represent values from -4 to +3. I mean, if you calculate, you will see that that's the range of represent. Because obviously, you can imagine, see, it is intuitive to understand, right? There are only, if I say 8 combinations, right? I can either make it from 0 to 7, so I have 8 unique things to represent. If I want to talk about sign, it shifts from -4 to +3. If you count -4, -3, -2, -1, 0, it's 5 already. Then 1, 2, 3. So totally you get 8 values to represent. So what you understand is the patterns are only 8. Either I can represent 0 to +7, or I can represent -4 to +3, right? But I'm not going to all the details here. But you can actually try this out. I would encourage all of you to take a few examples, try writing in binary. So it's actually good to get comfortable with binary, because as an embedded programmer, the reason I'm stressing this and talking about binary numbers is embedded system programmers have to be comfortable with binary, because you will look at device registers, you look at signals, you'll read a register where some signals are coming, that register will be encoded in binary. You'll have to look at individual bits of the register. So understanding binary and being comfortable with binary numbers is important. And there's also an associated thing which you actually can look at. I'll talk about it quickly. So this we already saw, size of the binary string. I just gave you an example, right? If you have 32 bits, you can see the example here, right? 32 bits, I'm splitting it as 4 bits here. So this is the biggest number I can represent in 32 bits. All ones is the biggest number, right? In any binary pattern, all ones is the biggest number. And if you calculate it, you will get this value, 2 power 32 minus 1. That is the number that you can represent here, okay? And typically when you talk about CPUs, this is what we refer. 32-bit CPUs means all registers are 32 bits. Today most microcontrollers also support 32-bit operation. Very low cost, some of them you still get 16-bit, 8 bits are there. But many of them modern microcontrollers, they support 32-bit for many computations actually. So longer the binary string, more bits you have, the bigger the numbers that you can process actually, okay? Now, I talked about, I'm not going to explain in too much of detail, but I talked about it already. If you can represent -5, right? There's something called the 2's complement notation. I'll probably quickly go through this example here. Okay, so if you want to say represent -5, right? So you actually minimum need 4 bits to represent, right? So you start with +5. If you want to represent -5, you first start with +5. Okay, +5 using 4 bits, you can represent like the 0, 1, 0, 1 is +5, because it's 2 power 0, which is 1, plus 2 power 2, 4 plus 1 is 5. To represent -5, what we need to do is we'll start with this. Okay, then we will do what is called flipping all the bits, which means flipping is just change all the bits from 0 to 1 and 1 to 0. So the 0, 1, 0, 1 becomes 1, 0, 1, 0. Okay, then you add a 1 to this value. So you have to do what is called the binary addition. When you add, you will get 1, 0, 1, 0 plus 1. This 1 will get added to the least significant bit. So when you have a binary string, so the rightmost what you write is called as the least significant bit. These are terminologies again an embedded programmer should understand, because when you read a data sheet, they will talk about LSB, bit position 0. Bit position 0, LSB is generally same in a computer, in an embedded processor. And this is called the MSB, okay? And this is called the LSB. So when you add 1 to the LSB, you will get this value 1, 0, 1, 1. So 1, 0, 1, 1 is called as the 2's complement representation of -5, okay? So in a 2's complement notation, by looking at the first bit, you can tell whether it's a positive or a negative number. If somebody tells you this bit pattern is in 2's complement notation, so because you see a string of bits, right? We'll see later also. To interpret that bits, you should know what form it is encoded. If somebody tells you this 4 bits, it is representing something in 2's complement notation, you have to only look at the first bit to know whether it's a positive or a negative number, right? So first bit is 1, MSB. When I say first bit, I mean MSB I'm talking about. If MSB is 1, it means it's a negative number. How do I get the value? I know any quantity has got both a sign and a magnitude, right? I know the sign is negative. How do I get the magnitude? The same procedure is done. So you take this 1, 0, 1, 1, right? Okay. I saw this 1, I know it is negative, so I can just go and write minus here, right? After that, I don't worry about it. Then what I do, I just again flip the bits. So if I flip all the bits, I get 0, 1, 0 and a 0, and I add a 1. So I'll get 0, 1, 0, 1. Now for this I calculate the magnitude. I do 2 power 0 into 1 plus 0 into 2 power 1 and 1 into 2 power 2. I get the quantity 5 here. So I have put minus already. I just put the 5 here. So that is how I get minus 5. So you understand how a 2's complement notation, if somebody tells you this is representing a 2's complement value, you know it represents minus 5. If I told you 1011, I am telling you it is not 2's complement, it is just normal binary number, then what is the value for that? It's not minus 5, right? Then I have to take this bit also to the magnitude calculation, right? Then the value will be different. It will be what? 1 plus 2, 3 plus this 8. This will be actually 11. We're getting the difference. So this distinction is important to understand. So what you have to really understand is, when you talk about binary patterns, right, you'll again now we'll quickly see one more thing. It is important to know what it represents. Ultimately, it is all the programmers. I mean, if I view a string of bits, if I treat it as a positive number, it means something. If somebody tells me it is being treated as a 2's complement number, it means something else, right? It's either 11 or minus 5, depending on what I want to do with it. And when you look at microprocessors, the way they do things also is like that. For example, if you have things like multiplication and other operations, right, you can have a signed multiplication or unsigned multiplication. So you have two different instructions. Yes, unsigned multiplication instruction, if say a 32-bit processor, it will take all 32 bits as a magnitude and do there's an algorithm for that. It will do that multiplication taking all 32 bits as just the magnitude. Whereas if I take a signed multiplication, right, in a signed multiplication you have to worry about minus into minus is plus, plus into minus, all that, right? So there is a different algorithm for that, and that algorithm will treat that number in a 2's complement notation. So it knows this is a signed quantity, it's a 2's complement notation, and the algorithm works based on it. So basically inside a computer, you tell the computer what to do. You might have stored something in memory. I might have stored 1011 in memory, but unless I tell the computer what it is, it doesn't know how to treat it. If I have, as a programmer, I have stored it thinking I am storing a negative number, I have to tell the computer that is a 2's complement notation quantity, treat it that way and multiply that number. If I am treating it as a normal unsigned quantity, then I will use the appropriate instruction. Is that clear? So it's important to understand, because when you see just a string of bits, right, it's the interpretation what we give, the programmer decides how he is storing and he tells the computer to treat it in the proper way. Is that clear? Okay. We have figured out, we started this talk about how things are easy to do in digital, right? We just now saw how to represent numbers in digital. I mean in digital form. When I say digital, you can say it's meaning binary, because two states. How does this binary translate to digital? Because some of you might have studied things like circuits, transistors and all that, right? You can build what is called as a flip-flop using a few transistors, and you can, giving some inputs, you can make the output to be either 0 volts or 5 volts in a TTL logic, right? So I'll say 0 volts means it represents bit 0. 5 volts means it represents bit 1. So as long as I can represent two states in a stable fashion using hardware, then I achieve, you can say, 1-bit storage, right? I mean, this is the way computers are built, right? I'm able to store in a flip-flop 1 bit, which means I have a 1-bit storage device. If I have 8 flip-flops together, and if I set them in individual values, like zeros and ones appropriately, and I can say I have an 8-bit register to store a particular quantity. Are you getting the way the computers are built? So basically, with transistors, it's easy to build a device to store 1 bit. You put a group of them, you can store n number of bits, and you treat them together, you are able to represent a binary word. Is that clear? So now we have achieved how to store a binary number in hardware, because ultimately inside the computer you have to keep remembering it's all voltages and that's what is stored. So zeros and ones are stored as 0 or 5 volts or whatever, and they are in a stable fashion in a flip-flop. So I am able to achieve storage of a number in the hardware using the voltages which are in a stable state. Now once I have done that, there are algorithms, there are circuitry that you can build to easily build things like addition, subtraction. Then using those basic units you can do multiplication, division. All these can be built in digital hardware. Some of you might have studied in your electronics courses or whatever, right? Single bit adder, full adder, half adder, and you can then Booth's algorithm to implement a multiplier. There are, I am not going into the details here, but those of you who are interested, it's good to study some of them. The reason why we are going into all these details is it's good to understand how a computer operates, because as an embedded programmer, you'll have to be able to relate to things when you see some hardware, how the interaction happens. So it's get a good idea. So this is how a computer is put together. So inside you can build all these circuitry. All these are part of what is called as an ALU inside the CPU. Every CPU will have an ALU where you have these adders, subtractor units, all that. They're all put together and they function together. You tell the ALU to do add, it does an addition. You tell it to subtract, it subtracts. How we tell the ALU to, we'll see quickly. Okay, but you understand ALU is a block of hardware. It has some inputs. Imagine, you can say, we'll talk about later. You can imagine some input lines it has got. You tell it to add, it'll add. You tell some signals to, you give some different set of signals, it'll do a subtraction and things like that. Comparisons. You can build all using circuitry like that actually. Okay, so and many other operations, like you have a binary bit pattern, you want to shift it, you want to do binary digital logic, right? You want to mask a particular value, you want to add a particular AND or AR or a particular bit value to another value. All those operations are possible because nothing but Boolean logic, and you know how to build digital circuitry to do AND or and stuff like that. So all those are very straightforward to implement in hardware. So this much you are understanding. Now we have seen how to represent numbers, right? Now the other thing which computers do is to process textual information, right? We often deal, I'm using a PPT, which means I need to be able to process text. So this text is stored in some form. How is text stored? So first thing you have to understand is inside a computer you can only store binary values, right? Nothing else, there's no other form of storage available in a computer. Only zeros and ones can be stored, which means text also has to be encoded and stored in binary form, right? So how do you do that? So we came up, the scientists at the time, they came up with a way to have a standard way of storing information, which everybody agrees upon. So this is where codes like ASCII came about. Then when multiple languages were supported, they expanded it. But ASCII was a simple code, so they only worried about the English for ASCII. So they took the English language world where English was the predominant language. So they said, okay, we'll come up with a standard encoding for ASCII. So they took the English language characters, lowercase, uppercase, and all the typical keys that you see in the keyboard, like comma, space, hyphen, question mark. For all the characters that you see on the keyboard, they came up with a code. A code is nothing but again a binary number, right? So this is where this understanding is important, right? Ultimately, everything is a binary number, right? And to take an example, right? What is a code for A? I'm giving this example here, right? The number A, small letter A, is represented by this bit pattern. Okay. So this bit pattern, if you convert it to decimal, it is if you treat it as a number, it is 65. I mean, commonly if you see a ASCII chart, you will actually they'll just say A is 65 in decimal. But ultimately, it is nothing but this bit pattern 01000001. So this is what is stored inside. So if the set of bits, if I tell the computer it is an ASCII value, for example, you are trying to print something on the screen, right? How does it happen? I'll have to tell the computer, for example, when this word is printing this screen, there's a lot of processing which happens inside, right? Ultimately, information, this page is stored as ASCII text. Maybe some formatting characters are there, but it is ASCII text. And there is a lot of software inside which takes that ASCII symbol for yes, it does a lot more processing. It sends some bit pattern to it has something called a font. That font is used to display it on the screen. So a lot of things which goes on inside, ultimately to translate that code into what you see on the screen. Even if you take this A itself, right? This A inside, if you open this file, this A will be stored as this binary pattern in ASCII. Okay. So when Word or the PPT reads that file, it has got this A, and it will do a lot of things to display this A on the screen in the form that we see. It's doing fonts and stuff like that, it is displayed. So what is important to understand is ASCII is also nothing but a binary code, because inside the computer, you can only store values in binary. But that's why I said the interpretation is important. Somebody tells you what is this. If I tell you it is an ASCII code, you will say it is A. If I tell you it's a number, unsigned number, you will say it's 65. So what you treat with is ultimately depending on the program, right? So you will see some example. When we go to C, I'll illustrate this difference, right? Storing a bit pattern. Based on what you tell the printf function to do, it will print different things. In the memory, only say this bit pattern is stored. If I tell printf to treat it as a ASCII character and print, it will print A. If I tell printf to print it as a number, it will print 65. We will see those examples when we get into C. But for now, we understand text is also stored in the binary form. There is a standardized code called ASCII for that, and it's a sequence. A is 65, B is 66, and so on. Then you have again symbols for capital A to capital Z. Numbers are stored like, I mean, the ASCII, when you say 0, there is an ASCII code for the symbol 0, right? Because when this word is displaying the 0 here, there's an ASCII code for that also, right? The number 0 is different. ASCII symbol for 0 is different. ASCII symbol for 0 is actually 0x30, which is actually 48, and 48 decimal is nothing but ASCII code for 0, and 1 is 49, and so on. So there are things for it. So basically, ASCII is nothing but a code to store textual information. Is that clear? So the same bit pattern, how you interpret, gives you the meaning actually. Okay. Now let's move on to. Similarly, after ASCII, when computing spread all over the world, there are so many languages. India itself has so many languages, and ASCII was just a 7-bit code originally. And some number of characters that we have in many Indian languages, 7 bits you cannot represent. 7 bits only gives you 128-bit positions, right? But many Indian languages have 200 plus characters, or if you go to China, it's even larger, right? So they came up with a code, standardized code worldwide. All the countries got together, they discussed, and they decided a code called Unicode, which is a multi-byte code. I'm not going to go into the details, but all you have to understand is Unicode has more bytes. It's not a single byte. It's not just 7 bits. But there is no standardized code to represent all the languages in the world. All the known languages in the world are represented, and that is how modern operating systems like Windows, modern Linux, everything supports Unicode. So that's why you're able to conveniently edit in multiple languages on the standard desktop actually. Okay, so that is how the world is processing today. Today, most computer systems will support Unicode. Unicode is the standardized form to represent all the languages in the world. The original thing is there's a backward compatibility with ASCII also. So ASCII and Unicode, the ASCII ranges will overlap. So there is no problem in reading older files also. It means the same, even if you treat it as Unicode actually. Okay. Now let's move on to understanding. We have seen how to represent numbers, how to represent text, and we have understood that okay, inside a computer you can actually build basic units to do things like addition, subtraction, multiplication, comparisons, and all that. And you can take, by comparisons, you can actually implement some logical actions and so on. So now let's look at putting all these things together. How a CPU typically operates, right? Okay. So in any computer, you have a CPU which is actually having this ALU, and what the ALU does, inside the ALU there is something called as a control unit. Okay. And attached to the CPU, you have a memory. Okay. The memory is where your program is stored. We'll look at what is program. Program is nothing but instructions. You will quickly see that also has to be stored in binary form, because everything inside a computer, inside the hardware, is all in binary form. So instructions are also nothing but bit patterns which have some meaning for the ALU. Okay. So what the control unit does, which will be continuously commanding, what is first thing which is called as a fetch cycle. Fetching is, this is the RAM here. RAM is nothing but your random access memory where all your program is stored. Program is stored in binary form, which is again nothing but a sequence of bits. Maybe for a simplicity's sake, let's assume each byte is one instruction. I mean, let's assume a very simple computer where one byte has one instruction. So the fetch is nothing but instruction is read from memory. It comes inside the computer register. There are some special registers, and then from there is something called as a decoding. The decoding actually takes that instruction, that bit pattern, and it decides what that instruction is telling me to do. Maybe let's assume that computer is very simple. It has only 4 or 5 operations. It knows whether to add or subtract or whatever, and it may read some data again from memory to operate. Then the control unit generates all the signals, and it causes the execute cycle then it gives all the required information to the ALU, which is both the data and the decoded information for the ALU to do either an add or a subtract or multiply. Then the ALU will actually complete the processing. Maybe it will store the results back into some registers or RAM or whatever, and then immediately the next cycle of fetch will start. So this is called as a fetch, decode and execute cycle, and it keeps, the CPU continuously keeps doing this all the time. So it will start at one location. The moment, typically when a CPU is powered on, right, CPU will jump, most CPUs will jump to one fixed address, because memory is addressed, memory is nothing but a sequence of bytes. Each byte has got an address. So typically, if you power on the computer, you need to have some meaningful instructions to operate. That is why most CPUs will start operating from a non-volatile memory region. So for a particular CPU, it may say like, okay, it will always start executing from address 0. So the designer of the system will make sure at address 0, there is a fixed non-volatile memory, a ROM or a flash or whatever, which doesn't lose the contents when the power goes off, so that there are meaningful instructions that CPU will start executing. So that's called as a bootstrapping of a CPU. So CPUs will typically start operating from the ROM region or a flash region where meaningful instructions are there. That will typically be a small program. They'll first start executing, they will initialize all the other peripherals, then they may go and read a bigger program, maybe from a disk or whatever, right? Even if you look at your PC when it boots up, it starts with what is called as the BIOS, which is there in the ROM. That in turn loads the operating system, then gives control to the operating. The operating system will get loaded to the RAM, which is a much larger amount of memory in a PC, and then so typically embedded systems also do the same thing. Sometimes you may just execute from the flash or ROM itself, some small embedded systems, or sometimes they'll copy the code from flash memory into RAM and give control to the RAM to execute. But the moment the control starts, the CPU keeps doing the same thing. If it starts at address 0, it will go to address 1, 2, 3, so on in sequence, unless there's a special instruction which tells, no, go to address 100 and start executing there. That is called a jumping or whatever, right? You'll see that. So that's what it does. That's what we are talking about here. So it'll read, say, instruction, say it starts at address location X, it will read that instruction, it will then decode the instruction. It decodes the instruction here. Decoding is nothing but, I said that instruction is nothing but a bit pattern. It tries to interpret what the instruction is asking it to do, and then it will generate all the signals to the ALU to execute that instruction. Maybe as a result of the execution, you have to store the results back, maybe into some registers or memory or whatever. Then you immediately go to the next instruction, which is say at address X+1 and repeat the process. So any CPU in the world, this is what it keeps doing, which is called the fetch, decode, execute cycle. And the only thing which will change is called the control transfer instructions, which will make the CPU do something not immediately. It may say jump and do that set of instructions which is stored somewhere else in memory. And control transfer instructions can do that based on some conditions. Maybe only when this is satisfied, jump. Otherwise, continue like that, right? Okay, you'll see examples of that as we go into the other CPUs. But is that clear? What a CPU does? CPU, inside a CPU, that's called as an ALU, and there's a control unit. Any CPU will need memory where it fetches the instructions. It starts at some address, and the execution will keep going in sequence till some control transfer instruction comes to place. Is that clear? So that's called as the fetch, execute, decode cycle of a CPU. And now we'll quickly look at this instruction encoding, right? I talked about instructions are also nothing but binary patterns, right? Now, when the CPU starts executing, when it fetches, say from address 0 it fetches, it got some bit pattern, okay? Now let's assume ours is a very simple CPU, okay? We have only, let's say it has only 8 bits, and it has only 4 operations possible, okay? Assume it fetches 1 byte at a time. But this is a very simple CPU I have designed, an experimental CPU. I can only do 4 different operations, which are like add, subtract, multiply, and divide, okay? And for 4 operations, you can intuitively now know, like, okay, based on the bits and binary things that we understood, 2 bits are enough to specify. So if I just have 2 bits, I can say this can give 4 different patterns, which can mean 4 different things. Okay, so out of that 8-bit that I read from the memory, I can assume the lower 2 bits, right, which is bit position 0 and 1 here, are going to encode whether it is a add or a subtract or whatever, and that is good enough for my ALU. So all that hardware will do is, it read that 8-bit quantity, and you can intuitively understand, right? I mean, some of you might have studied hardware. If you have, for example, let's say I have my ALU block here, okay? I'm doing this ALU block. This is my ALU, okay? And this ALU takes 2 inputs, okay? Say some X0 and X1, okay? And this ALU, assume it has some connections to some registers, okay? Register 0, it has another connection. Sorry for my drawing. It's not too nice. Let's say it has 2 registers, okay? And it has 2 inputs, and it can do only, inside it has got multiple circuitry. It has probably got a, say, adder circuitry. I am just blowing up this ALU here. It has got a subtraction circuitry. Maybe both could be same. If you have done hardware, you can implement in the same circuitry. Let's say it has multiply and say divide, okay? Assume the way a CPU would be typically implemented is, assume each of these can take 2 inputs, okay? Register 0 input and register 1. I'm not showing all the pins. Assume each is 8 bits, okay? Each are the 8 bits line, R0, R1, okay? All of them they're connected to both the registers, assume, okay? And you can have a very simple, the simplest way to do it would be, all of them may be computing everything all the time, okay? And you can actually use these 2 bits of your instruction, right? I said I have 2-bit instructions, which are add, subtract, and so on. I can have something like a multiplexer here, which gives out 8 bits from one of these 4, and these 2-bit can be decoded and given as an input to control this. So basically these 2 bits, all it does is selects the output of the adder or the subtractor or the multiplier or divider. Okay, that is what, I mean, I'm just maybe trivializing things a bit for you to just understand what instruction decoding really means, just to get a sense of it. So 2 bits of the instruction can be just used to control what goes to the destination register. Maybe it adds up, maybe all these 4 units may be even working, because it may be the easiest way to implement, right? Just hardware, all the data goes, all of them compute and have a result ready on the output port, but I only choose what I want based on the instruction. So I mean, just giving a very simple example, modern CPUs have a lot more instructions. They may use things called microcontroller, microprogramming and all that, but at a lowest level, this is what happens. So basically an instruction decode, nothing but data is available, the CPU has to do certain operation, some bits of that instruction tells you, probably in a typical encoding, if I have say 8 bits, some bits may be opcode, sometimes some bits may tell you which register, so register 1 and register 2, 2 registers to operate, right? 2 bits may tell what registers are the operands itself, and so on. And finally, the CPU will take those and use it. So I'm just giving you a very quick view of what happens. I mean, don't have to worry about too much details, but for you to understand what is instruction, what is that encoding, right? Because everything is binary. So when you treat that bit as an instruction, that is what happens inside the CPU. Those bits control what really happens in the processor. Actually, is that clear? So we'll move on from this. So this is how an instruction encoding happens, and as I talked about it here, right? The other bits can tell maybe which instructions are used. Sometimes you may have a multi-byte instruction where the first byte is the opcode. The next 2 bytes may actually be the address of the operand. So those are called, different addressing modes you have in the CPU. The next 2 bytes will actually be address from where the data has to be fetched, and so on. Okay. So this is how a typical CPU operates, and this is what we mean by instruction encoding actually. And so we talked about memory. Memory is organized as bytes. Okay, modern memory, all modern computer systems, memory is organized as bytes. A byte is nothing but 8 bits. So when you say organized as, what do you mean by organized as bytes? The lowest unit I can address is a byte. 4 bytes of data from memory have to be read, and bits at a time. Bits. So when you say organized as, what do you mean by organized as bytes? The lowest unit I can address is a byte. If I give an address, I get 8 bits at a time. Okay. So if I have to read 32 bits, which means the data comes, if I have 32-bit register, when I read from memory, 4 bytes of data from the memory have to be read, and that is assembled together in my 32-bit register actually. Okay. And here again, it's important to understand as an embedded programmer. I'll probably, I don't know if I have a slide on that, but I'll probably just explain that quickly, because right? I said 4 bytes are from memory, right? I mean, assume I have a register, which is a 32-bit register. Okay. So this is byte 0, this is byte 1, byte 2, byte 3. Okay. So the 32-bit register has to be read from memory. Now I say, assume this is my memory here. Assume somewhere here I have stored a 32-bit quantity. Okay. So let's say this is address x, this is address x plus 1, this is x plus 2, so x plus 3. I'm just writing it in hexadecimal values. Okay. I have to probably talk about hexadecimal also. Let's say I have these values here. It's a binary, I'm just representing it in hexadecimal. I'll cover what is hexadecimal. Hexadecimal is a quick way to represent binary. Okay, so hexadecimal, if I say 1 to hexadecimal, you can easily take each of these and expand it into binary. So 1 is 0001 and 2 is 0010. So this 8-bit binary value can be quickly written in hexadecimal by taking 4 bits together, or one nibble is called 4 bits. It's easy to remember also. So programmers, embedded programmers use hexadecimal often because binary is too long to write, right? So you can just take 4 bits at a time. 4 bits are values from 0 to 9, and then what we call ATF. We use 16 symbols in hexadecimal, so it's easy to represent. So you can quickly represent a value. So this is the way it is, right? Now, when I'm trying to load this 32-bit register from memory, right? So if it is stored like this, okay, and the value comes inside the register like this in this sequence, where the least significant byte, this is the LSB, gets the value from the lowest address. So from address X, 4 locations are having the 32-bit quantity. If the lowest significant byte, the least significant byte, gets the value which is stored in the lowest address, then the next byte gets from the next address, and the most significant byte gets from the topmost, highest address. This kind of a pattern is called the Little Endian architecture, because this is important to understand when you deal with registers and stuff like that, and how you store a register and read back in an embedded system. So this architecture is called Little Endian. Intel CPUs, for example, our PCs are all Little Endian. Little Endian is more popular these days, but there are computers which are using what is called as Big Endian. In the Big Endian architecture, this is reversed. What will happen is, this will be 1, 2, 3, 4. It will be completely reversed. So what will happen is, in the Big Endian architecture, the least significant byte will be stored, in the highest address actually. So this is called as a Big Endian architecture. Big Endian architecture, there were CPUs. Olden days, companies like Motorola used to make systems which are using Big Endian architecture. Intel has been Little Endian for a long while. There are some chips, today where the Endianness can be selected at a reset time. There is a pin which will tell you, whether the chip will behave in Little Endian. The whole hardware is designed that way. But Little Endian, most CPUs like Intel and all are Little Endian. So in Little Endian, this is how the 32-bit register is mapped. It is good. It is important to understand this because as an embedded programmer, sometimes you'll be reading a register and you may need a 32-bit register and you are storing it into memory. But later, you may want to only look at the lower 8-bit values of that register. Then you should know where in those 4 bytes I should go and take the 8 bits which is of interest to me, right? So as an embedded programmer, you need to be aware of endianness. Maybe if you're doing a general purpose computers, you probably don't have to worry about all these things. But as an embedded programmer, sometimes you'll deal with these kind of things, so it's good to know how it is mapped. Okay. So if it is a 16-bit quantity, also same thing holds. If it's a 16-bit register, there's only 2 bytes. So then assume this is a 16-bit quantity. Same way you will see 0x12 here and 0x34 here. Is that clear? What is endianness? So endianness is good to understand because as an embedded programmer, you may sometimes need to deal with it actually. Okay. So when you look at memory, how data is stored, 32-bit register read, this you need to be aware actually. Now we'll just look at a simple instruction sequence. You know how all these come together, right? We looked at how instruction decoding happens, encoding happens. So ultimately, inside the computer, whatever we write, right, at a high level language, whatever language we write, finally you do what is called as a compilation, and finally that C program or whatever is converted into assembly language, or it has to be converted to the binary instruction that the computer understands. Binary, it's all zeros and ones, so we use something called as an assembly language. But assembly language is nothing but binary language in a human readable form, right? For every, if you look at the assembly language, for every instruction here, there is an equivalent encoding in binary. Instead of saying 01000, I am writing MOV, but there's a one-to-one mapping. So assembly is nothing but a one-to-one mapping in English for each of those operations that the basic microprocessor supports, right? So something like, for example, if I want to add a sequence of numbers, right? In assembly, it gets translated to something like this. For example, I'm storing, for example, I want to add say 10 numbers, right? I will start by storing in a register called the accumulator. It's a special register where all the computations are finally stored. I store the value 0 here. Okay. Assume my numbers are stored from address m plus 1 and so on. That is where my numbers are stored in memory. So my algorithm, simple algorithm will be something like start with address m, read address m, and store it into register b. So move is an instruction. So like arithmetic logic and all that, there is also typically data movement instructions in a CPU, which are used to move from one register to another, or from register to memory or memory to register. Assume my instructions, my data is all in memory. I first read this first location in memory where my first number is stored. I store it into register b, and there is an instruction called add b. So assume my CPU is such a way, one operand is always in what is called as an accumulator. The olden processor, if you are familiar with 8085, there is something called as an accumulator, which is always part of add instruction. So what this will do is it will add b, the contents in register b, to the contents of register A, and the result will be stored in register A itself. Okay. So now I had initially had value 0 in register A. Now 0 plus the first number, that result is now available in register A. Okay. Then I go to address m plus 1, read that value, move it into B, then again add B to A. So now I added the first 2 numbers. I keep going on like this till I finish all the 10 numbers. Then at the end of that sequence, you can say the 10 values have now got added and the result is available in the accumulator. And that I can probably store it into another register to store the value. So this is just an illustration to show how a typical microprocessor works. To translate something like a high-level problem like adding 10 numbers, I might have written code in C, but finally it gets translated into assembly and it will appear something like this. You'll see more enhancements. Here I'm writing same sequence 10 times. This is where concepts like loops come into play. If you see the same sequence, right? Move, add, something like that. The only thing which changes is the address, whether it is m plus 1, m plus 2. So you can logically think of making this program shorter by actually maybe keeping this in some other register. I can keep the address itself in a register. I read that from that register, treat it as an address, read the value, put it into B, add, then increment that register. That register, if I increment, address has got incremented, right? So you get the idea. Then I can have something called as a loop construct. This is where the control flow instructions in an assembly language will be useful. I can probably have a counter. So if I want to add 10 numbers, I'll have a counter. I'll initialize the counter to 10. And I'll keep decrementing the counter as soon as I add. As long as the counter has not become 0, I will say jump back and execute the same sequence again. Before jumping back, I will increment the register which points to the address. Are you getting a sense of it? Because it's good to have a view. Because when you work in embedded C, you will treat like concepts like pointers and all that. If you understand this, it's very easy to understand what really goes on. Because when you read anything from memory, you use ultimately an address is generated and a pointer is nothing but an address. Okay, so that's why I'm just going into a little bit of detail here, so you understand how finally a microprocessor operates. When you deal with embedded systems and embedded C, you deal with pointers a lot. It's good to understand what happens. Okay, so is that clear how a typical program is converted into assembly language? And you see a sequence here. This entire sequence can be maybe made shorter by using something called as a loop. And a loop is where you need other instructions like control, transfer, jump, branch, or a loop, and all those other instructions come into place. And you may have to check some conditions. That is where there are other registers called control flags or condition flags in a typical CPU. You can compare things. Comparison is nothing but subtraction, right? If I have a counter, I keep counting down. When it becomes 0, then I know there's a special flag which is called a 0 flag. Then I can check that and take a decision. So this is how you develop programs. Ultimately you have to remember anything you write in a high-level language like C ultimately gets translated into assembly language like this. That is done by a compiler. Compiler knows how to understand the high-level language and translate it into the appropriate. So you'll have a compiler. The target processor is important. If I have to compile for ARM, the compiler has to generate ARM assembly or ARM machine code. If I have to compile for Intel x86, the compiler has to generate x86 machine language. What is the difference? Because machine language is unique to the processor. The bit patterns will be different. Add in ARM may have a different encoding, whereas add in x86 may have a different encoding. Okay, that's what the compiler's job is. The front end of the compiler is a common, but the back end where the machine language is generated will be specific to the particular processor which is there. Okay. So we have seen the normal sequence, right? We have seen how instructions are operating. We have seen it goes in sequence unless you have a control transfer instruction. I didn't go into the details. Any processor will have something like jump or branch, which means jump to some other address and start executing there. And the jump can be unconditional, which means just jump, or sometimes it will be conditional. Conditional means it will check certain things. The condition is true or false, it will then jump. So that is how you implement loops. A loop in C is ultimately translated in assembly using those conditional instructions actually, okay? Then there are something called subroutines where there's say another sequence of instructions which is repeatedly used. So you can, you can say call that. A call always has a return. I want to go execute the 10 instructions and come back here. So that is where you use an instruction called a call in assembly. It will go execute that instruction. It will then come back to where the call instruction was there. So this is how functions in C are implemented in something like an assembly language, right? So basically, for many features in assembly, a high-level language, there is support available in the assembly level, in the machine level to implement those functionality. Okay. Now those things are mostly under programmer control. Now for an embedded system, you have one more thing which is called as interrupts. So we'll finish this and we'll kind of a couple of more slides for this module. What are interrupts? We have seen an interrupt. We saw a typical embedded system. We say there is a sensor. We talked about the water level controller, right? The water level controller. Suppose the tank became full. You want the CPU to immediately take some action, right? The CPU has to immediately do the job. The CPU is normally running a program. How does it know that it has to stop and turn on the motor? So this is where some external pins on the chip are called interrupt pins. And suppose there is a sensor for the water level sensor. When that water level reaches that level, that sensor will output some voltage, say 1, and that pin is connected to the CPU. These are called interrupt pins. And the CPU, as course of its execution, it will keep checking that input at the end of every instruction. So I am running some other normal program. I finished one instruction, say the move instruction, I go check that pin. Now I see that pin has become 1, which means there's an external interrupt, some condition that I have to service. Then it jumps to something called as an interrupt service routine. There's a special code. Immediately the instruction will stop, whatever it was executing, it will halt, it will jump from there to a special instruction. That is where, for example, our code can be there. That instruction now will go and check, oh, is this sensor, which sensor is it? It is the water level sensor. The sensor is now true, which means the tank has become empty or full or whatever. Either they turn on the motor or turn off the motor. All that action will typically be driven by the interrupt service routine. So these are called interrupts, and this is what is typically used in embedded systems to build all your controls actually. Any embedded system will have interrupts, lot of interrupts, and there may be nested interrupts, level priorities for the interrupts. Those are all complications that you learn when you go into a system, but interrupts is a basic mechanism by which external devices indicate that it needs attention and action. The other thing is called as an exception. Exceptions are things which happen when execution is happening, when the instruction itself, for example, I access an invalid region of memory, right? There is no address, there is no memory, no contents there. Then the processor will indicate saying, something wrong happened, then the program has to be aborted or something. Or I try to divide by 0, which is called as a divide by 0 exception. Or sometimes I added 2 numbers and there is an overflow. The CPU cannot deal with it, right? All these are called exceptions. Sometimes processors will have different priorities of execution. I may be in a user level, but I want to do a system call or something. I'll use something called as a trap instruction or a system call instruction. They all generate an exception. And whenever a processor exception happens, again, control gets transferred to what is called as an exception service routine, which is again a piece of code which immediately starts executing. So these two things are, you can say, a little, asynchronous in some sense. Interrupt is completely asynchronous. Exceptions at the end of every instruction you can get an, exception condition, and it needs to be dealt with actually. Okay. And the conditions, if suppose a process created a divide by 0 exception, what will happen is the program will be killed. That particular program will be terminated. That's what the operating system, you will see a message saying divide by 0 exception, process killed or something in your system, and the program execution stops there. Okay. So we will kind of stop here. So this module was to give you a overview of what a typical computer does, how a typical CPU operates. We started with the basics of what is a digital computer. We looked at what a typical CPU does, which is a standard fetch, decode, execute cycle. We also quickly looked at how a simple CPU can be designed by instruction encoding, how a 2-bit can be used to encode, and then how that can be used to, we also looked at a simple piece of an assembly code where a set of operations can be implemented in assembly, then compilers translate things into assembly, and then we also looked at interrupts and exceptions. Interrupts are especially important for the embedded system because that's how external devices are able to indicate to the CPU that I need attention, and real-time systems, it's very, very important because when the interrupt is generated, you have to service that interrupt within a few milliseconds or microseconds as the case may be, and that's how systems are put together. There are other things called exceptions which happen sometimes when a special instruction is executed or the instruction encounters an error like a divide by 0 or a floating point error or so on. So we'll kind of take a break here. We have looked at the basics of what a CPU does, how it registers and so on. We'll stop here. In the next you'll again now look at some architectures like ARM and RISC-V, and then subsequently you'll look at an example of a typical microcontroller in a little more detail. What are the different blocks, why it is used, for you to get a sense of how to typical microcontrollers features that are available, how you can build a system out of it.